All right, more on buffers. Keeping going and talking about some other problems that you might see for buffers that aren't just straight off a titration curve, although partial neutralizations always lead to buffer solutions, so keep that in mind. So here we're going to look at reviewing a little bit and doing some buffer problems. One thing you need to realize about a buffer solution is it actually falls under the umbrella of the common ion effect. If you think about it, the shift in equilibrium position that occurs because of the addition of an ion already involved in the equilibrium reaction. So you have the acid, when it reacts with water, it makes a little bit of your conjugate base. But if you add a salt that has the conjugate base also to the solution, now you're adding in a common ion. So basically it becomes a Le Chatelier's principle application. Adding in the conjugate means it's going to shift, and you're going to, like I said, get a new equilibrium position from that. So common ion effect applies to buffers, and it does have an equilibrium position, and it's manipulated through the Le Chatelier's principle. Let's look at an example here. Hydrocyanic acid reacting with water gives you hydronium and cyanide. You're going to produce a little bit of the cyanide and a little bit of the hydronium. That's what you do when you're just doing regular weak acid equilibrium here. You dump the acid in water, it creates the little bit of percentage that ionizes, really small amount. But if I add in the salt, this is a salt that has the conjugate in it. Remember, sodium cyanide is always soluble because sodium happens to be alkali metal, and they're always soluble salts. So basically, if I add sodium cyanide here, I'm really adding in cyanide. Then it's going to shift to the left, and it's going to make more of this. And when it shifts to the left, it's going to also remove or consume some of the hydronium. So that's going to change the pH. It's going to stabilize the pH a little bit. So the pH will definitely be a little higher because you've technically added a base to your solution. The solution of the hydrocyanic acid and the sodium cyanide is now going to be less acidic than just the hydrocyanic acid alone. So it's going to make the pH go up a little bit. Less acidic, remember, pH goes up. It's farther away from 0 and closer to 7, which is neutral. So keep that in mind. Same thing is true if you're creating a basic buffer. You have a basic buffer that's like at a pH of 9. You add in the base, you add in the conjugate acid salt. Now your pH is going to drop slightly and become more acidic in that particular case, due to the Le Chatelier's principle and the common ion effect. All right, so let's look at a buffer system that has been created from ammonia. We have ammonia and ammonium in solution floating around. We have this buffer pair. So if we introduce hydrochloric acid to it, the hydrochloric acid, of course, is going to break apart into HCl and Cl minus because it completely dissociates. Which one of the buffer components is the HCl going to react with, or the hydrogen going to react with? Is it the ammonia or the ammonium? Which one is it going to react with? Which one can actually accept an H? Yes, the ammonia can accept the H. If you think about it here, the ammonia adds in the H, that's going to make more ammonia. But this is the key part here. You remove your H pluses from solution. That keeps the pH from changing too much. It keeps the pH from changing very much here. if you pull that hydrogen out of solution, now the pH is going to stabilize and be very close to what its original pH was. That's why the buffers can resist pH change, drastic pH change. Looking at the other component, if we added hydroxide to it, sodium hydroxide, which one is it going to react with? We added that to the system, which buffer component is going to react? Is it going to react with the ammonia, or is it going to react with the ammonium? Which one can give away an H here? Because the hydroxide is going to be the base here. It's going to accept the H. So out of the two in the pair, which one's able to give away an H? Yes, the ammonium gives away the H here. So if you look at it this way, the ammonium will react with the hydroxide and then you will get ammonia, right? Of course, you get the water also as the byproduct over there, because this donates over here and you end up getting the water. And then the remnants, okay, the NH3 left over. But what's the key significant part? Is you're removing hydroxide. Removing it from the solution. If you remove hydroxide from the solution, that means the pH won't go up dramatically. It won't shoot up. So this is how the buffer maintains the pH range and keeps it from doing drastic changes. Drastic changes. It's very important not to have a good set of buffering components and buffer system if you want to maintain a certain pH range. Now here are the calculation review again for the buffers. You have your original buffered solution and then you have your modified pH over here. And this shouldn't be too much different. It's very close. Very close to the original pH. Shouldn't be too far off. I mean, I'm talking like if the original pH was like 4.5, it should be like around 5 or around 4, somewhere in there. But not, it shouldn't have shot up to 9 and it shouldn't have gone all the way down to 1. It should be very close to its original one. Now, let's do the stoichiometric calculation to determine the new concentrations. Or in our case, we'll find the new moles. We're going to use the BCA chart for that. Okay, the BCA chart's important. Now, that's step 1. You got to do the BCA chart if you have a buffer. Step 2, you can use the Henderson-Hasselbalch equation, which is the easiest. Okay, once you figure out your moles in solution, you can do that. However, there is a second option. You can do equilibrium calculations using the common ion effect, where you add it in to the initial parts for both. The common ion effect way actually takes longer. It is still something, though, that you can use. I'm going to show you an example of how to do the common ion effect again, because we did them in the KSP problems. But once again, the Henderson-Hasselbalch is the quicker way to go. It's faster, it's easier. But say you get confused and you start setting it up like equilibrium, you can just throw it in and do the common ion effect and that will still work. So looking at our nice chart here, we've got to remember the ratio of the buffer components. We like them to be 1-to-1 here. And when you add the H, the conjugate goes down. The acid goes up in the pair just slightly, and you can see it slightly gets off. That's what changes the pH just slightly. Over here, you add the hydroxide, the acid goes down, the conjugate base goes up. Once again, it's pretty close here to maintaining the original pH. They haven't changed too much, so it's resisting this pH change. So let's look at this first buffer problem. Let's go ahead and do this one. This is just a regular buffer problem, and it tells you it's a buffer solution. It says buffer solution. This is easy enough. If it tells you it's a buffer, you can go straight to the Hendy-Haas. Use the Henderson-Haas-Leblanc equation. We have 0.45 of acetic acid, 0.85 of sodium acetate. So we have both in solution. We know this is a buffer. So really, just pH equals the pKa plus the log of the base over the acid. This one's an easy one because it's telling you it's a buffer. It's just a plug and chug. So negative log 1.8 times 10 to the minus 5 plus the log of, now look for the base, 0.85 over the acid, 0.45. And we will get our pH over here. So you calculate that. Negative log 1.8 times 10 to the minus 5 plus the log. Now what you should also be examining and looking at is the base component is a little bit higher in concentration than the acid component. If this was 1-to-1, then the pH would equal the pKa. Okay, so if the pH equaled the pKa, this is where it would be 4.74. If they had equal amounts of the buffer components, but we don't have equal amounts of the buffer components. We have slightly higher of the base, so our pH should be slightly higher than that 4.74. And it is, because you should have gotten 5.02, right? But is it really that far off? It's really not that far off. It really did not move too much, okay, for this buffer solution. Okay, with a little bit more base in there, it's going to buffer around this 5 pH here. Not too difficult. Easiest buffer problem there is going to be. Now, we just went over this too, and we talked about it back in the drawings. If you have equal conjugate acid-base pair, equal amounts, remember this is going to be the log of 1, which turns into 0. So this gets canceled out of the equation. So you end up with a pH equaling the pKa. Like so. You already know this. That's how that works. And talking about buffer capacity, really want those buffer components to be equal, so that will maximize your ability to the ability to resist the change in pH. So what is the buffer capacity? It's the amount of protons or hydroxide ions that the buffer can absorb without a significant change in pH. So that is a buffer capacity. How much can it withstand before it has a dramatic change? So it's determined by the magnitudes of the acid and its conjugate, the base pair. Like how many components are in there, how much buffer component is in there. Buffer with a large capacity contains large concentrations. Large capacity must have large concentration of the acids and the bases in the buffering components. And like our body, where we have a couple of buffer systems that keeps our blood pH around 7.3 or 7.4. The main one is the bicarbonate system, but our system has a way of maintaining really large amounts of those components so that our blood does not shift too far out of that range. 7.3, 7.4, if it goes too low, because usually the only time the things that will get buffered out will be acids, because we ingest lots of acidic food and drink. Don't really ingest a whole lot of bases, but you do ingest a lot of acids, because, you know, like soda and coffee and anything that's tart probably has an acid in it somewhere. But the pH of the blood gets maintained by this bicarbonate system, and the body does a good job of maintaining large components of it, so the pH doesn't drop too far. If it drops too far and stays too far low for too long, you get acidosis, which is a condition, of course, where your blood pH is too acidic, and then that it results later on in, if you don't catch it and it doesn't get treated, you know, you're going to end up with organ failure. All right, so optimal. What is optimal in terms of our buffer capacity? Large amounts and concentrations of buffer components, and you really want that ratio to be equal. You know, an equal amount of acid, equal amount of base. Large concentrations, equal ratio. You know, 1-to-1, acid to base here. As you can see in the picture, the concentrated buffer has more buffering components. That means it can withstand more of the attack from an H plus or an OH minus. So a concentrated buffer can neutralize more than the dilute buffer. So in order to, you know, have optimal buffer capacity, you need to have large amounts, large components, moles of your buffer, which would be the acid and its base, or the base and its acid. And you need to have, you want to get that ratio as close to equal as possible. Now, buffering, buffer solutions, and different things are going to occur at all different pHs. And you create a buffer as to which pH range you need to maintain. But that is all dependent on the pKa of the weak acid in the pair. Okay? pKa of the weak acid, that's going to give you an idea of which pH your buffer is going to end up being around. Like the bicarbonate buffer is right around 7, because it's the pKa of carbonic acid is right around 7, a pH of like 7.2 or something. So the pKa, you know, if it's a very weak acid, then it's going to buffer in like the 9s or the 10s. If it's a stronger acid, you can buffer around like the 3s or the 2s. So finish the notes for next week. I'll post them on Monday, so you'll be able to crank them out. We only have a few more problems to do in the buffering, and work on those titration problems and the particulate model diagrams.